Hi, today I will try to talk about Windows 32 priority separation, a mechanism that is probably very famous for the most of you. I will try to answer on what, why, and likely how. The agenda for today include what is quantum and context switch, how to change the Windows 32 priority separation value, explaining the Windows 32 priority separation mechanism, if are there any limits to the values I can experiment with, latency results and FPS results by testing all those values. Let's start with the process scheduling. We have 10 slides about this. I borrowed the title of those slides from Windows internals, and I think it's more precise and accurate to give this title as process scheduling because actually Windows 32 priority separation is about process scheduling. What is quantum? A quantum is the amount of time a thread is permitted to run before Windows checks to see whether another thread at the same priority is waiting to run. If a thread completes its quantum and there are no other threads at its priority, Windows permits the thread to run for another time. So if after the current thread or process we haven't something else on the same priority, then the quantum will execute it again, will run again on the current thread. And that's the definition from Windows internals if you want to check it. Now let's see an example to understand better what we described. Let's take for example that we have new processes that they born. They schedule to execute from the CPU. The CPU will define by Windows 32 priority separation because the quantum is actually the value of Windows 32 priority separation, and according to the priority level, it will start executing each process that he has to execute. And after that, it will terminate each process after he done the job. And we saw how quantum work. Let's talk now about context switch. Context switch is every time the CPU transitions to a new process, a context switch occurs. When we're moving from the process A to process B, this is called context switch. Let's see this very simple example. On the right side, we have the CPU flow. We have the process P1 and the process P2. Now, the CPU is executing the first process, the process P1. The CPU eventually receives a signal to interrupt the process 1 and execute another task named to process 2. For that reason, the CPU will save the state of process 1, the job until now that he have done, including the data and instructions stored in registers and the cache memory, and the CPU will load the state of process 2 of the new process that from that he received the signal, and encompassing its data and instructions. The CPU initiates the execution of process 2, and after when he's done with the process 2 is completed, the CPU saves the state here. The CPU loads the save state of process 1, and the CPU resumes the execution of process 1 from the point where it was interrupted. So when we finished, sorry for that, when we finished we temporarily stopped working on the first process. When we finished with the process 2, we came again to the process 1 to continue the job and finish the execution of the process. So this is how context switches work. Controlling the quantum, how to change the Windows 32 priority separation value. I think it's more precise to say controlling the quantum because the value is the quantum that we define with the help of Windows 32 priority. To change the setting, right click this PC icon, alternatively Windows Explorer, Properties, Advanced System Settings, Advanced tab. Click the Settings button in the Performance section and click yet another Advanced tab. Let's see how it works. Sorry for that. Open File Explorer, right click, Properties, Advanced System Settings, Advanced. And here we have two dialog boxes to choose between programs and background process services. to choose where we want to focus to give more performance in programs or background services. And you can choose how to do it. All right. The dialog box contains two key options. The first is the programs, and have the value 26 hex and 38 decimal. It's the same thing, that just in different format. This setting designates the use of short variable quantums. We will talk shortly about those what those definitions, about what they are, which is the default value for client versions of Windows and other client versions like Xbox, HoloLens, and so on. If you install terminal service on a server system and configure the server as an application server, this setting is selected so that the user on the terminal server have the same quantum settings that would normally be set on the desktop client system. You might also select this manually if you were running Windows Server as your desktop OS. This is the definition from Windows internals. And now about the background services, again the format in decimal and hex. We have value 18 and 24 in decimal. This setting designates the use of long fixed quantums. Here we had short variable quantums, now we have long fixed quantums, the default for server systems. The only reason you might select this option on a workstation system if you were using the workstation as a server system. However, because changes in this option take effect immediately, it might make sense to use it if the machine is about to run a background or server style workload. So what we also learn from here, when we change this option, taking effect immediately, so you don't need to restart your system. Anyway, so it might make sense to use if the machine is about to run a background or server style workload. For example, if a long computation, encoding, or modeling simulation need to run overnight, you could select the background services option at night and return the system to program mode in the morning. And again, from Windows internal. So as you understand from here, which value you will choose, it depends from your needs. It's obvious, but you can just choose between those default values that Microsoft gives, and you've done here. You don't need to experiment or do something more. You can choose between those values and decide where you want to focus. Variable quantums table describes. Let's see also the table. Tables describes the exact quantum values. Recall that this is stored in a unit representing on 1/3 of a clock tick. So when we have a clock tick, is the 1/3 of this tick. And here we have the table that will be selected based on the quantum index and which quantum configuration is in use. Thus, when a Windows brought into the foreground on a client system, all the threads in the process containing the thread that owns the foreground window have their quantum triple. Threads in the foreground process run with a quantum of 6 clock ticks, whereas threads in the processes have the default client quantum of 2 clock ticks. I want to mention that inside this table, the numbers here represent the ticks, 1/3 of the clock tick. It's just the numbers that representing this part. Okay. And as I said, we will talk shortly about variable, fixed, and what all those stuff means. So in this way, when you switch away from a CPU intensive process, the new foreground process will get proportionally more of the CPU. This is because when it's thread run, they will have a longer term than background threads. Again, assuming the thread priorities are the same in both the foreground and background processes. We saw that before this. We need to have the same thread priority from a thread to another thread. You need to have the same priority, the same thread priority. Let's explain more simple about this table. Short quantum index used for threads not IO bounds, don't get stuck waiting for data. Quantum value depends on the thread priority level. Higher priority, larger quantum value, more execution time. Long quantum index used for IO bound threads frequently waiting for data. Quantum value depends on schedule or configuration, variable or fixed quantum. And variable quantum value increases with IO activity, and fixed quantum value remains constant. Okay. Quantum settings, registry value. This is actually the path that you can find the Win32 priority separation, and let's see it here. If you open a registry editor, um, and let's do it from the beginning, choose HK local machine, system, current control set, control, scroll down, priority control, and you can define the value that you will select. You can see the hexadecimal format and the decimal. Currently I have 24 hexadecimal value, and you can just close it and it will take effect immediately. Besides determining the relative length of thread, quantum short or long, the registry value also specify whether variables quantum should be utilized along with the priority separation, which as explained dictates the quantum index when variable quantum are enabled. The value consists of 6 bits divided into 32 fields. So this part described here. We have 3 fields of 2 bits, short versus long, variable versus fixed, and priority separation, fields of the Windows 32 priority separation registry values. This photo also is from Windows internals. Short versus long. Opting for a short quantum means the CPU allocates a brief period to applications, promoting faster task switching. From the other hand, choosing a long quantum allows applications to utilize CPU for extended periods, resulting fewer interruption and smoother processing. So, with short quantum, we have faster task switching. With a long quantum, we have fewer interruptions, and that means we have a smoother processing, which is particularly beneficial for server systems. Variable versus fixed. Fixed quantum ensures that time is evenly distributed among applications, whereas a variable quantum allows certain applications to use the CPU for extended periods when necessary. Opting a variable quantum can enhance gaming performance, potentially leading to better FPS by allocating more CPU time to the game. On the other hand, a fixed quantum is conducive to improve inputs, which means to reduce the latency, as the CPU time is equally shared between the game and process responsible for input devices. This part means if we have Fortnite, for example, as a process, and we have also the processes that they're controlling your input devices like your keyboard, your mouse, your headphones, your microphone, the CPU time is equally and shared, so the same execution time will have the game process and the process that are responsible for your keyboard, mouse, and so on. And the priority separation, this field is stored in the kernel variable. PS priority separation sets the priority separation, which with values ranging up to 2. Priority boost for foreground threads after waits. As will be described shortly, whenever a thread in the foreground process completes a wait operation on a kernel object, the kernel boosts its current node base priority by the current value of PS priority separation. The windowing system is responsible for determining which process is considered to be in the foreground. As described earlier in this chapter, in the section controlling the quantum, PS priority reflects the quantum table index uses to select quantums for the threads of foreground applications. However, in this case, it's being used as a priority boost value. The reason for this boost is to improve the responsiveness of interactive application by giving the foreground application a small boost when it completes a wait. It has a better chance of running right away, especially when other processes at the same base priority might be running in the background. And those are the definition from Windows internals. But let's explain it more simple. When a thread in the foreground process finishes waiting for something in the operating system, its priority gets a temporary boost by a value called PS priority separation. This boost aims to help interactive applications run more smoothly, giving them a better chance to run immediately after waiting, especially if other processes with the same priority are running in the background. Now let's see the Amit table. I think you know who is Amit. This is the table, and here we have a short description. Now we can understand almost everything on this table. Let's start with this part. As you see, we have all possible values that we can choose. We can put in Windows 32 priority separation as a quantum. We can put only those values here. We have hexadecimal format, the decimal, and the binary format of each value. We have the interval, the length. We have already described what long means, what short means, what variable means, what fixed means. Ignore PS priority separation part, this column, ignore it, I will explain it on the next slide. And let's also focus on this part. Sorry. We have the foreground quantum, background quantum, and total quantum. The total quantum is if we do the math between foreground and background quantum, and we have this result. The foreground quantum is the CPU time used to foreground programs by foreground programs, and the background quantum, the CPU time used by background programs. A total quantum is the total CPU time used. Now let's explain the PS priority separation. Enhancing focus on foreground applications or not. The PS priority separation, if we have the value 0, no foreground boost, value 0. The no foreground boost value will allocate time equally 1 by 1 between foreground and background processes, which means we have the same time in foreground and background, not more in foreground or not more in background. The medium foreground boost, which has the value 1, the medium foreground boost value will prioritize real-time application like your game with ratio of 2 by 1. So it will focus, it will give double time to your real-time application than the background process. And if we select high foreground boost, which has the value 2, the high foreground boost value will make the CPU spend 3 times, 3 by 1 more time on the foreground application compared to background services. So you're choosing between 3 options. Every foreground option represents a specific value, a specific quantum. And we could say that theoretically, if we are gamers and we want to prioritize real-time application, we will choose a value that include medium foreground boost or high foreground boost. Windows 32 priority separation values. Now, after we talked about everything related with Windows 32 priority separation, we can understand and we can read this table. Here we have again all possible values with their description. The short, fixed, for example, we have short, fixed, high foreground boost. You can understand what that means. We have long, fixed, high foreground boost. And now it's more easy for you to understand what every single option means, every single value. Now, Windows 32 priority separation limitation values. What values can we use only? Here is Amit to help us. According to the documentation of Windows allows up to, this is the 63 decimal, and because the bits mark is made up for 6 bits, so why the value above this exists? What happens if we enter a value greater than the theoretically maximum allowed? According to the answer of Amit, why can't you put values greater than 63 in decimal? In the Windows 32 priority separation registry key, when anything higher is treated the same as value below the maximum limit, the deal here is that the highest value in reg D word can hold this. This is the binary format. In decimal, this is the value. Windows doesn't restrict user from entering illogical values, and when the kernel reads the value that we have set it in Win32 priority separation, it has to handle these weird values. So it reads only part of what you enter specifically, the first 6 bits of the bits marks. This means value over 63 just loop back. Let's explain it more simply. Let's take this example. Suppose a user decides to set the Windows32 priority separation registry key value to 80. In binary, the representation of 80 is 10, 10, 30. However, since the system reads only the first 6 bits due to the constraints of the reg word, it considers to be this representation without the last 0. So when we have a different binary value, we have also a different decimal value. Now, converting this binary representation back to the decimal, we have a new value, 40. Instead of encountering an error or rejecting the seemingly illogical value of 80, the system adapts by effectively looping back to a value within the acceptable range. So, despite the user inputting 80, the system interprets and treats it as if it were 40. So, what we understand from here is we can't set a different value, a greater value than 63. And for that reason, you need to use only between those values. You can't, there is no reason to select any other value than those here. Okay, let's move now to the practical part of this talk. Let's see the latency results of all values that I tested, the latency capture and analyze with Windows Performance Toolkit, and also you can see the Google Sheet here. I have in depth every single test that I did and which driver I tested. Here I tested the CentOS kernel driver, and you can see everything here. Just I chose to put everything in PowerPoint to be more easy for you to understand the results. Let's start with average duration fragments. I tested everything in Fortnite only. As you see, the best value is 24 and the worst is 26. All values are in hexadecimal format, and for that reason I haven't mentioned something about this, but all values are in hexadecimal format. The average exclusive duration has as a winner 24 value and the worst value was 28. In average inclusive duration, the best value was again 24 and the worst 18. In sum duration, the best value was 1A and the worst 25. In sum exclusive duration, the best value was 18 and the worst 26. In sum inclusive duration, the best value was 18 and the worst 26. In conclusion, in terms of latency, the best value was 24 with the most wins, and the less wins had 1A value. In FPS part, the FPS captured and analyzed with CapFrameX. The average FPS was the best on 2A value, and the worst was with 14 value. 1% loss was best in 29 value and worse with the 14 value. 0.1% loss was best with 24 value and worse in 15 value. Adapted vested dev FPS doesn't mean the FPS. This metric doesn't represent the FPS. Just it's something related with the latency. So the best number was with value 15 and the worst with value 18, 28. In smoothness, we can't say that we have any bad value. All values have the same result, just for the needs of the PowerPoint. The worst values was 14, 15, and 18. All the other values was the same. In part of stuttering, again, we have the same concept. All values are basically the same, but the best values was 16, 1A, 24, 25, 26, 28, and 29. The frame times were the best in 24 and 29 values, and worse in 14 values. 14 value, sorry. Now invariance is smaller than 2 milliseconds. The best value was 2A and the worst 28. in variance is smaller than 4ms, the best value was 28, and the best was 28, and the worst was 22a. The variance is smaller than 8 ms. The best values was 24 and 29, and the worst 2a. Variance is smaller than 12 ms. The best values was 24, 26, 28, and 29, and the worst 14. Variance is higher than 12 ms, was 24 with 0 number. It's not actually 0, but for the needs of the PowerPoint, I just put the 0. It was actually 0, the number. But in comparison with the other values, we actually have the same results. We can't say that we have something better. All values are on the same range. So in conclusion, the best values in terms of FPS was 24 and 29, and all the others were worse, that we could say. So in conclusion, based on results, best value was 24 hexadecimal, and in decimal is 36. For further reading about this topic, you can check Tech Power Up Windows32 Priority Separation, that has a very interesting PDF. You can read Amit's research, and this research showing more things in code part, more programming stuff about this topic. Of course, you need to read Windows Internals book. You can just read the pages that are talking about the topic. Blurbusters link that talking about the Windows 32 priority, and you can read xbitlabs.com that they made also a very good job about Windows 32 priority. And lastly, processor scheduling and quantum windows, another article about this topic. And we come to the end. Thank you everyone for being on this video. I hope you now to understand this mechanism. If you have any question or you want to discuss about something, please leave your comment and I will try to respond.